So now let's concentrate a little bit about conservation laws. So there are two main types of conservations. One is a conservation of mass and the other one is a conservation of energy. The first one we're going to talk about is the conservation of mass, which is given by the continuity equation. So in order to explain it, let's talk about how fluids move. Fluids can move or flow in many ways. Water may flow smoothly and slowly in a quiet stream or violently, like when it goes over a waterfall. Air may form gentle breeze or a raging tornado. To deal with such diversity, it helps to identify some of the basic types of fluid flow. So the general characteristics of fluid flow: fluid can be steady or non-steady. It could be compressible or incompressible. Fluid flow can be viscous or non-viscous, and fluid flow could be rotational or irrotational. Note, this is a very good picture that everybody should concentrate on, and the idea behind this is when you're talking about fluid flow, it not only depends on how the fluid is flowing, but where it's coming from. So if you notice that the stream at the bottom and at the top are going to be very different. So it depends on the pressure inside the container and how much the fluid can flow. So steady or unsteady fluid flow. Steady flow is defined as when the velocity of the fluid particles is at any point is constant as the time changes. Unsteady flow exists whenever velocity at a point in the fluid changes as time will pass. So equation of continuity is a very important equation. So in order to explain what equation of continuity is, I have to ask you a question. Have you ever used your thumb to control the water flowing from one end of the hose to another? And the answer probably is yes. And so in the two situations, you will see water flow like this or water flow like that. And what is the difference? The difference is when you hold your hand in front of a hose, what you are doing is you are decreasing or reducing the cross-sectional area that the water is able to flow through. When you decrease the area that the water is allowed to flow through, it actually increases the speed of the water to counteract what you are doing. And that, in fact, is the basis of equation of continuity. So the idea is that when objects move from smaller cross-sectional areas to larger cross-sectional areas, their velocities decrease. However, if they move from larger cross-sectional areas to smaller cross-sectional areas, they will tend to move faster. And mathematically, we know that the mass flow rate of anything, which is change in mass over change in time, is given by rho, A, and the velocity of whatever you're doing. And the volume flow rate is given as delta V, delta volume over delta time, is given by AV. So combining all of these terms together, the continuity equation can be given as rho, which is the density, area, which is the cross-sectional areas, V, which is the velocity, equals, at any 2 points, rho 2, A2, and V2. If the fluid is incompressible, then rho 1 will equal rho 2, and we are only going to deal with A1, V1 equals A2, V2. In a nutshell, the equation of continuity is described in this slide. So rho 1, A1, V1 equals rho 2, A2, V2, where rho 1 in this case, because it's not really changing, will remain the same. So velocity 1 and velocity 2 will be related by this expression right here. So now let's do a problem that relates to it. A garden hose of inner radius 1 centimeter carries water at 2 centimeters per second. The nozzle at the end has a radius 0.2 centimeters, so it's actually getting smaller. How fast does the water move through this constriction? So in this example, they are giving me a garden hose. And they are saying that R inner for this garden hose is 1 centimeter and velocity is 2 meters per second. And for the nozzle ahead, they are giving me R equals 0.20 centimeters, and the velocity of water is what I'm going to be looking for. Okay, so right away there is a centimeter here. What are we supposed to do? Divide it by 100 centimeters times 1 meter. So I get 0.01 meters. And for here, completely the same thing. Divided by 100 centimeters will give me 0.002 meters. Okay? Now how do I solve for V? What I know is from the continuity equation, rho 1, A1, V1 equals rho 2, A2, V2. Right? Now, between the garden hose and the nozzle, the density of the substance is not going to change. So this is going to be equals to 0. That means A1 V1 equals A2 V2. In general, the cross-sectional area of anything is given by A equals pi r squared. That's just a standard formula. So I'm going to plug that in. Pi r1 squared V1 equals pi r2 squared V2. Okay? Same thing here. Pi's are not needed. And all I have to do now is plug in R1, which in this case is going to be 0.01 squared, V1, which is 2, equals R2, which is 0.02 squared, V2. Now rearrange it and calculate what the answer is going to be. Mine comes out to be 50 meters per second. But you should confirm it for yourself and make sure that I'm actually getting the right answer. The next conservation law is the conservation of energy, which is given by Bernoulli's equation for fluids. So Bernoulli's equation is basically given as points, the difference between point 1 and point 2. The conservation of energy states that the energy at point 1 should equal the energy at point 2. And for fluids, the energy is given by the work done per unit volume by the fluid, plus the potential energy per unit volume of the fluid, plus the kinetic energy per unit volume of the fluid. At both of these points should equal the same. So P1 plus rho g y1 plus 1/2 rho v1 squared should equal P2 plus rho g y2 plus 1/2 rho v2 squared. So now let's do an example of this kind. A nozzle is connected to a horizontal hose. The nozzle shoots out water moving at 25 meters per second. What is the gauge pressure of water in the hose? Neglect viscosity and assume that the diameter of the nozzle is much smaller than the inner diameter of the hose. This question gives me that I have a nozzle and I have a hose. And they are both horizontal. If they are both horizontal, that means there is no change in potential energy of my system, right? Which is going to be a very useful idea. And also, since these are horizontal, I won't have any atmospheric change. So delta P is going to be 0. So my potential energy is going to be 0, and my change in the atmospheric pressure is, my change in the pressure is not going to be a factor. Okay, so now what do I know? From Bernoulli's equation, I have P1 plus rho GH1 plus 1/2 rho V1 squared equals P2 plus rho GH2 plus 1/2 rho V2 squared. So this is my potential energy and this is my potential energy. Since the change in potential energy is 0, these two will go away because H1 is equals to H2, right? Since H1 equals H2, I can pretty much get rid of these two terms. What am I left with? P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. So now P2 is given to me as atmospheric pressure, right? So that means P1, which is the gauge pressure, minus P2, which is the atmospheric pressure, is what I'm looking for, right? Which is now going to be equals to 1/2. I'm going to combine these two terms together, rho V2 squared minus V1 squared. Okay, so I combined these two terms together. So what are we given? I am given that V2 is equals to 25 meters per second. but I do not know what V1 is. Now that is going to be an issue. Now how do I counteract that? Well, I have one more equation that I might be able to use, and which is called the continuity equation, right? Okay, so the continuity equation says A1 V1 equals A2 V2. Okay, this means A1, so if I was to find V1 will be A2 over A1 V2, right? This means this is going to be pi r2 squared divided by pi r1 squared times V2. Pi gets canceled. I will have r2 squared over r1 squared. So r2 squared over r1 squared V2. Now, we know that the question gives me that the nozzle shoots out water moving at 25 meters per second. This means assuming the diameter of the nozzle is much, much smaller than the inner diameter of the hose, this term is going to be very, very tiny. So with respect to V2, V1 is almost can be assumed to be 0. Okay? This means if this is almost assumed to be 0, this goes away. What am I left with? I am left with delta P that I'm looking for. Delta P that I am looking for will be equals to 1/2 rho V2 squared. That means rho for water is what? 1/2 1,000 kilograms per meter cubed, and V is given to be 25 meters per second squared. You plug the values in and you solve them. So for this one time, the answer is that I get is 3.1 times 10 to the 5 pascals. And what I want you to do is to convert it into atmospheric pressure and see how much of a factor that's going to make.